Hi everyone, good morning. This is Ming Yao from Singularity Engineering, and I'm happy to be here today to talk about solder joint reliability. So this is a webinar. Normally my webinars are more demo based, but this one we're going to switch it up a little, and we're going to talk a little more about the how we develop solder joint reliability simulation models and how the models work. A little bit about our company. Singularity Engineering is a certified Ansys channel partner based out of Oakland, California. We typically primarily serve Northern California. We provide Ansys software sales, support, as well as training to our customers locally. And we're happy to be working with many companies nearby on various solder joint reliability, PCB reliability, and other issues. In addition to this topic, we obviously support the full portfolio of Ansys tools. So we have capabilities on structural mechanics, so like fatigue and reliability simulations. We do lots of fluid dynamics analysis, bioprocessing, chemical mixing, aerodynamics, and electronics cooling. And we also do quite a bit of work on the electronic side, everything from PCB signal integrity to antenna design, antenna optimization, and antenna environment interactions. But today we're going to focus on solder joint, which is something that I've been doing for a long time. And like I said, it's primarily going to be a presentation. Hopefully, it's informative to you. I'll try to show a little bit of demo at the end here, at the end of the webinar. I'm having a little bit of trouble with my streaming software, but it should the presentation should go okay here. All right, so let's make sure it's updating. Yeah, okay. So the fundamentals of solder joint reliability, we're specifically going to focus on kind of a narrow aspect of it. This is so we're going to look at solder joint reliability for BGAs due to thermocycling. So solder joints have a few different failure scenarios. Thermocycling historically has been the one that causes the most failure. High power chips tend to generate a lot of heat. When a part is heat up, if you have a mismatch in the thermal expansion coefficient, so we have a material on top that has a low thermal expansion coefficient, and the material on the bottom has a high one, when you heat it up, it'll tend to bow out like this, right? The top kind of doesn't expand as much as the bottom part, so we bow out, and then we cool it down, it'll bow the other way. So you can think of it as a cyclic loading. You kind of bend, due to thermal loading, you're bending this PCB uh, assembly back and forth repeatedly, and this will cause solder joint to fail over time. What you will see is the impact of this is if you, instead of imagining two pieces laminated together, let's imagine the top is a package and it's connected by solder balls to the yellow part, bottom of the package. Um, so over time, you will see a crack start to appear, and it will start to grow across the solder ball and causing it to fail. So this is just one way in which solder typically fails. This is again very important for high power products like central processors, GPUs. It's often for high power systems, so any type of desktop, server, or automobile based system where you have a lot of processing. This could cause damage and reliability issues over time. The other source of failure for solder joints are vibration and shock. So I'm not going to talk about that today, but perhaps we can do that in a future discussion. So vibration, oftentimes for automotive applications, we worry about vibration, so random vibration, shock due to crashes and impacts or potholes. And for mobile systems, usually the power is fairly low, but then the package is very thin. So sometimes, depending on how powerful your mobile chip is, you may need to do solder joint analysis, but also drop is very important for mobile reliability. But today we're going to kind of stick this with one topic of thermocycling induced solder joint failure. The way solder joint failure occurs is that the damage will accumulate. So solder joint reliability involves cyclic thermal loading. In real life, this means turning it on, turn it off. Every time you turn on a chip, it'll heat up. over time, which causes heat to dissipate and causes the entire structure to deform. And when you turn it off, it'll hopefully cool it down. In test cases, we typically accelerate the testing. So in accelerated environmental test chambers, we would ramp the temperature up and down, -40 to +85 degrees, back and forth, to try to see how long it takes for the solder to fail. So this type of solder simulation is valid for both kind of in-use applications as well as accelerated life test applications. What you see is kind of this is a simulation of a damage plot on a solder. So if you have the solder and you cycle it for many cycles and you cut it, you'll see cracks that develop like this and like this. This is a typical solder ball that cracks. You can see that it's fairly near the interface between the solder and the material that's holding it above, and there's some cracking that will probably occur on the bottom as well, depending on the geometry. But the idea here is that we would simulate it and we could track the damage accumulation over time, over different cycles. So, each load would cause the stress to damage the solder more. So it may take a certain number of cycles for a crack to initiate, and after that, each cycle would tend to cause a crack to grow, and eventually um, the solder becomes unreliable. Right? There's less contact between the two materials, so signals may have issues. You may have severe signal integrity issues if there are gaps. Um, you may see that your high frequency chips need to be run at slower speed for it to work. And if you keep going on, at some point it'll just crack right through and you won't have a working connection anymore. Now this, if you look at solder cracks like this, it's on a very small scale. It's very similar to large scale cracks that we often worry about in mechanical analysis. So techniques like fatigue analysis has been around for a long time, right? Ever since the advent of the railroad and rail car, people have been worrying about cracks that grows through and cuts through the axle and causes rail cars to derail. So this has been studied extensively, and it's very similar, right? Fatigue is very mechanical fatigue looks pretty similar to what happens to a solder ball in that a crack grows across. So fatigue, most of you should probably know this, but we typically start with testing. Um, there's a small local elastic strain that builds up at the key areas, and this will eventually cause a crack to grow. And as we keep cycling, pulling on this bar repeatedly, the crack will grow and eventually cut across. So fatigue is also a progressive phenomenon. It's oftentimes difficult to detect before sudden failure, and evaluation of fatigue and durability of structures requires FEA models and load histories of the structure. So, um, and the way we do, so since most of you are probably familiar with fatigue, I want to talk just a little bit about how fatigue analysis is done. We'll contrast that with how solder joint fatigue analysis is done. So in fatigue analysis, we toss a piece of material into test machines. This is an Instron 8803 fatigue testing machine, and we cycle it up and down many times. And then we generate this type of curve. So you keep pulling on this until it breaks, right? So then you know that depending on how hard you pulled on it, that's kind of the y-axis, how much alternating stress you're applying to the material. You have a point of saying how long it's going to last. So if I apply this much stress to my bar sample, then it'll last this long. And similarly, for different amount of stress, you can see that the lower the stress is, the longer my sample will last. So this fatigue analysis is now a material property for this material. Then in the future, when we do a simulation, if we want to replicate that type of stress, we can say, let's do a static analysis and figure out what the maximum stress is at this location and compare it to our data table in here and say, okay, if the maximum stress is this value, then we can, for example, assume that it'll take this many cycles to fail. So that's a fatigue analysis, and most of you should be fairly familiar with this. Now let's look at how a solder fatigue prediction is done. Uh, we also, I think the thing that I wanted to highlight with this fatigue analysis discussion is that whenever you're talking about durability, you're always looking at how your simulation results correlates to some sort of experimental value, right? In the fatigue analysis, we know from experiment that a particular stress will cause failure or crack to grow at a certain for a certain number of cycles, which means we can, if we in a simulation figure out what the maximum stress is for each cycle of a load, then we can also look on this table and figure out how many cycles it takes for a particular part to fail. It's very similar for solder fatigue, right? Companies are already doing lots and lots of environmental testing. So this is a machine, an oven that you put your electronics in. It'll cycle the temperature up and down for a week or a month, depending on how extensive your testing needs to be. And you know how long it takes. There will be a point that says, okay, my chip has failed after a certain number of cycles. However, whereas in a fatigue analysis, we have a machine that can apply a certain amount of load to our material. In a thermocycling analysis, we're not applying a stress load, we're applying a temperature. So you don't really know what the stress is on your chip or what the strain is or anything about what the solder is actually experiencing. You're applying a temperature which causes your part to deform due to thermal expansion coefficient mismatch. But you don't really know what the stress is, what the actual solder is experiencing unless you do a simulation. So in solder analysis, it's even more important to do simulations because you don't know what say you know that in a particular temperature cycle, your part lasts 2,000 cycles, but you don't really know what's causing that, how much the part is deforming, what are the stresses and strains experienced by the solder. So in a solder fatigue analysis, first, when we do a thermocycling analysis, we also need to do a simulation of the solder and the material to calculate what kind of to get that data, right? In the fatigue analysis, in this one test gives us both the X number of cycles of failure, and Y, the amount of stress. But in the solder simulation, the thermal physical testing only gives us the Y value. What is the life of that solder? In order to understand what the solder is experiencing, we need to do a simulation because there's really no way you can measure a solder's, you know, uh, strain inside of a thermal chamber. Its solders are often very small and it's very difficult. So if we do a simulation of the exact part we're testing, then we can get a chart like this, right? We know how many cycles the package lasted and the amount of strain and energy and stress and in this case creep strain that we have. So then we can put a correlation together. This is one of the work done by one of the Amcor gentlemen. I think it's Saeed's work. And what this curve shows you is that for creep energy and accumulated creep strain and creep energy, we can have two lines that tells us how many cycles to failure. And it's a pretty linear line. So this person has done many different tests of maybe different temperatures, different um, same solder, different temperatures, and different maybe different locations, different sizes. And you can see everything falls nicely on this line. So we have a couple of coefficients here that tells us, given a specific amount of accumulated creep strain or maybe the creep energy density, we can figure out how many cycles it takes. So just to get the material fatigue data for a solder ball, we need to do simulation. Right? Without simulation, all you know is how many cycles it takes for a part to fail, and then if you want to improve it, there's no kind of feedback on what can be done to improve it quantitatively. You can qualitatively pick a better PCB, maybe high reliability solder, but to establish this type of data, you need to have both simulation, which generates the x-axis, and the physical testing, which generates the y-axis. Once you have data like this, in the future, when you do your next generation of product, or when you decide to switch up your PCB, maybe you decide to switch up your solder joint geometry, you can then analyze this based on this data. So if I do a simulation of this, I can say, okay, the area that I'm worried about here has accumulated strain rate by modifying my design or changing the temperature cycle or changing the material, I have dropped my accumulated strain from 0.1 to 0.01, right? And that results in an order of magnitude improvement in my mean life or number of cycles of failure. So this is kind of one of the key things you want to understand when you're doing solder joint fatigue, is that just to generate the material data, right? To get the fatigue curve, you need to have both the simulation data as well as testing data. Okay. So the main difference between, so that's one of the difference. The other main difference between metal fatigue and solder fatigue is this idea of creep. Solder works on solder is a metal that melts easily, right? This is why we use it to stick different pieces of metal together and conduct electricity. However, this means that when you're using a high power system, you may have operating temperatures that's close to melting, right? It could be 50% or higher of its melting temperature. When a metal gets close to melting, it experiences creep. And what creep is that if you have a material and you put it under constant load, so you imagine you have solder and it's at a high temperature and you pull on it, or you hang a piece of weight on it and hold the other side. What you see is that the strain will change. Initially, you have a lot of strain, and for a long time it kind of stays stationary, kind of stretches slowly, and then later on it kind of suddenly gets pulled up again. So because solder has a low melting point compared to the operating condition, creep will play a large role in the solder deformation. And you see this in testing, right? If you have a testing cycle like this where you drop it down to -40 and bump it up to 115 degrees, this is a pretty aggressive temperature cycle. You notice that the length of the dwell time is important. And the length of the dwell time, this is creep, right? This is kind of the changing of the temperature. But when you hold a solder at a fixed temperature for a long time, and the durability of the material changes, that's due to this idea of even though the load is constant, the strain is changing, right? The solder is stretching due to creep. So this means that, you know, in metal fatigue, we can look at stress and strain typically, just stress actually. And that allows us to do a great job of predicting how durable a material is. But in solder, stress and strain won't tell us what the the dwell effect is, right? It'll produce the same result if we do like a 10-minute dwell versus 60-minute dwell. So to capture that, we need to look at both plasticity and creep behavior. And this is why in the figure before I showed you, the graph was a function of accumulated creep strain. So now this is not to say that you cannot use stress and strain, right? You can still use these values. It's just that there's been lots of studies done that showed if you include plasticity and creep, you get more accurate results. So think of fatigue calculation as, the key thing you want to do is predict how long things will fail, how long things will take before it fails, which means you can find correlations in anything. I can look at the stress of a solder. I can model solder as a beam. I can model solder as full 3D elements. You can establish all sorts of correlations. It's just that the more physics you include, the more accurate it will be, the narrower the band of uncertainty, right? If you just look at stress and strain, maybe you have an order of magnitude estimate. So you can say, okay, by changing it, I see maybe 1,000. I know that by changing certain parameters, my strain and stress decreases, which will obviously increase the life of my solder. And then so it's good for comparing different designs. The other way to think about of it is that if I need to predict how long something will take to fail, if I just look at stress and strain, maybe I'll have an order of magnitude estimate, right? Maybe somewhere in the hundreds of cycles, or like if I use a very uh, high reliability, expensive PCB, I can probably get into the thousands of cycles, and that's kind of the estimates you can get. If you want to be very careful and very detailed and accurate about solder joint reliability due to thermocycling, you need to add plasticity and creep. So this is why you see most of the folks that's developing packages that looks at solder reliability, they typically would use a more advanced model, whereas teams that maybe are integrating uh, existing components and not adjusting for the solder shape or the package foot design, they will use a more simplified manner because it'll be faster to solve. So there are a lot of different ways you can use. You can do fatigue analysis for solders, but the one we're focusing on today is using a creep model to get the kind of the most accurate method possible for solder joint reliability. So now we have since we know creep and plasticity is important, let's take a look at the type of models available in Ansys. So Ansys has a whole host of creep models available, and this is mostly to give the people that use our tools the flexibility of getting the right data. You can see the most popular version of creep model for solder is the Anand viscoplasticity model. This includes viscosity, which is a creep part of it, as well as metal plasticity, which is a permanent deformation due to material yielding. Now, this viscoplasticity model has 8 or 9 parameters. Looks like for 9 parameters. So you can imagine if you want to you have a new solder and you try to correlate it to a to find the coefficients for a non-viscoplasticity model to understand how the solder deforms as a function of temperature, strain rate, metal plasticity, and creep. You have to do a lot of testing, right? So we expect that most people will try to gather this data from literature, and we would expect companies that make solder material to do this type of testing or partner with labs that do this type of testing to get the coefficients you need. Almost no company will go, no one that uses solder would go and do the extensive testing needed to gather all of this data. So by providing our users with a wealth of different models, now you can go ahead and use whatever correlations and material properties the company you're working with has. Another very popular and almost identical model is the generalized Garofalo model. These two models are actually very similar in terms of the equations they use. They just move the coefficients around a little bit. Generalized Garofalo model, you need to couple it with maybe a plasticity model or elasticity model to get all of the coefficients. So just the creep part here has 4 coefficients, and then obviously for elasticity you need a couple more, and for plasticity you need a couple more. So when you add it all together, we're still talking about 8 or 9 coefficients for the generalized Garofalo model. There are a lot of other models available, so if you find a really good correlation for your solder that someone has established, then you should go ahead and use that, and hopefully Ansys will have the right creep model available for you to just plug the numbers in and run the simulation. I should mention that you're welcome to, if you have any questions, feel free to put it in the chat. Let me open up my YouTube window on the other side here, so I can kind of monitor the chat in case someone has some questions. Um, oh, there is a question. So someone asked, how in essence, do you decide the height of the solder ball after the solder reflow process? You would want that's not you'd want the geometry. So um, typically, that's done by measuring the size of the solder ball after the reflow. Um, yeah, so feel free to throw in questions into the chat. I can kind of answer it on the fly here, or I can save it to the end. It's up to you. So this is an example of the solder creep model. This was popularized by Dr. Darveaux, who I think is a director at Amcor. They've done a lot of great work to characterize solder reliability, and obviously their job in terms of developing advanced packaging requires them to do a lot of testing and get this type of curves. So let's take a look at what we have here. So the Anand viscoplasticity model is the most popular material model. It's originally developed for metal forming applications, which means that it's good for metals that are close to melting, that you may be putting a lot of stress on. So it seems like it's a good fit. When they did did the testing, right? We have the constants for the Anand viscoplasticity model filled in. And what they did here was they did lots of testing at different temperatures, They look at the shear stress and the shear strain rate, and they measured lots of different material property to look at the correlation and find that this set of data provides good correlation for the shear stress and strain on the solder ball at the areas of interest. So at 132 degrees Celsius down to 27 degrees Celsius, it seems to have a good match, and this allows us to expand on it. You can see here the equation itself is a hyperbolic sine model with all the terms here fit into into the equation. This equation, I believe, is from the maybe one of the Ansys papers, or maybe it's probably from the Darveaux paper, but the Ansys documentation will have this information as well. So this is the most popular one, and because it's most popular, you often find lots of published data on different types of solders. So if you're looking at a lead-free solder, for example, this is a tin lead silver solder, which was the original paper was written in. But these days, all the new solders that people come out with, typically someone would have done the testing and experimentation to get the parameters you need to model this efficiently as a creep simulation. Um, Wrong screen. There we go. There are other creep models available. For example, you find data on a time hardening double power law, and there's another set of coefficients to plug into. So we have Young's modulus as a function of temperature. We have some coefficients for the strain creep rate. So you're not limited to just that one model. Fatigue is all about correlation. You want to establish confidence that you're able to capture behavior that you've seen in the past accurately. And if it means going to a different creep model, that's totally fine, as long as you have that correlation. And this is a Saeed did some additional modeling for tin, silver, copper. So solder. This is a lead-free solder. So there's a lot of paper published on this area. Um, so the next step is creep simulation results, right? So now that we have the creep model, let's look at what you actually get from its creep simulation. This is the type of result you get where this is the original Anand model. We have a quarter of a package here and some solder balls. And you can see that where the solder ball meets the pack, I've hidden the top package, but you can kind of see the red ring down on the bottom here. So where the solder touches the PCB and the package, the outer perimeter solder will see high creep strain getting built up here. There's a few things we want to notice here, right? It's the the very large creep strain occurs primarily at the interface between the different materials, so solder and package, or solder and PCB, um, which means that we run into the typical problem of a singularity value, right? There's very high creep right at the edge. So if we only look at the maximum value, this means that it's difficult to, then the result becomes very sensitive to the mesh. Every time I refine the mesh, that value can potentially increase, and that makes it difficult for me to do validation later on. If I have to make sure the mesh is always the same between one model and the next, as they change the size of solder, as they change the geometry, it becomes very difficult to set up models accurately. If I look at the average of the creep across the entire solder, then we get away from the stress singularity or the creep singularity value. However, we run into the problem of if I have a bigger or smaller um, solder ball, then my average value would change. So you don't want to use the average either. What we ended up doing, the recommended method for the recommended method from the paper by Dr. Darveaux is that you slice off a piece of the creep of the solder. So you only take the a 5 micron slice of the solder or something like that. So you always take the same slice of solder near where the creep is high, and you do a volume averaging of just that area. Right? This means you got to prepare the geometry properly so that you have always the same thickness of solder to average over for your creep analysis. This allows you to compare different sizes of solder, and it also makes it somewhat mesh independent. Having uh, very having slightly different mesh sizes won't cause enormous difference in the value. So the way we do creep result averaging is we accumulate, we sum up. You can see what we do is for each solder we split up the solder ball with two sections, the top section and the bottom section, where you expect failure to happen. And then from that you can do this volume averaging of either the strain energy density or accumulated strain rates. And has a benefit of preventing singularities from affecting your results, and also allows you to look at different sizes solder balls. I see a couple of questions came in. Can the same methodology be used for surface-mounted devices like QFN? Yeah, definitely. So BGAs and QFN are very similar in the way that they're attached to the PCB. They both use a sort of a surface-mounted technology. With surface QFNs, you would have a thinner layer of solder, but you can use exactly the same methodology. Where can we find a NAND constants for SAC305? So that's a lead-free solder, and SAC305 has been around for a long time. So there's lots of published data on the NAND constants. So it's there. We have a few papers. If you want to contact me, I can point you in the. Maybe I'll put in something afterwards. I'll try to find the paper and put it into the comments for this webinar afterwards, since people are probably looking for it. Do we simulate all the cycles or just a few cycles to extrapolate? You do. You would only need to simulate a few cycles to extrapolate. And that's what actually great timing, because that's what it says here. So there's an idea of creep stabilization. If you run the simulations, you can imagine if I want to do a actual thermal testing, I would have to do thousands of cycles, maybe sometimes tens of thousands of cycles to make sure I have the durability I need. We can't really do that efficiently in computation. There's no need, because when you run these simulations, you see the creep begin to accumulate over time. So this is one cycle. It's like a flat section, up, flat, up again. And then next cycle goes like that again. And what you notice if you kind of overlap the change from one cycle to another is that the first cycle is a red curve. Second cycle is a green curve, then blue, then purple. And you can see that by the second or third cycle, they kind of all lie on top of each other, which means we can extrapolate the idea that once we have the creep result stabilized to this constant cycle, we know the amount of creep strain that will change for a given cycle in perpetuity. So we can estimate how many cycles it takes for it to fail. So it's very typical for us to do 2 or 3 thermal cycles, and we always see the result tend to stabilize fairly quickly. Okay, so now we've kind of gone through all of the background of fatigue, creep, what makes solder different. So let's take a look at the actual solder fatigue correlation method. And there's different ways you can establish the correlation. Again, based on different amount of accuracy and kind of you can do easy correlation that's fast to establish, but it's more limited, or you can kind of go very detailed, do a very detailed correlation that's widely applicable, but will require more work. So both are totally valid, and this is another key part of what we need to do if we want to capture accurate simulation, accurate fatigue results for solders. So again, as I mentioned before, if we have thermocycling, we can figure out and we have simulation, we can get this type of data of how many cycles it takes to fail, and what the energy release rate is, or the creep strain in the solder in the area of interest. That's the x-axis. The y-axis here is a little bit different than what I showed earlier. This is a crack growth rate. So what Dr. Darveaux actually did was that he did thermocycling on a number of packages, uh, and with different amounts of failure. Then he actually cut and segmented or cross-sectioned many of the solder balls to measure the creep, uh, how far the crack has grown. So he has data on the crack length as well as the number of thermal cycles. So he may be having different parts put into an oven, right? Here, this is the same thermal cycling from minus 55 to plus 125, 2 cycles per hour, and he did many hours here. We have a number of different uh, points of results here. But what we have here is that for he knows that for a certain number of cycles, there's once you cross section the solder ball, you can measure how far the crack's grown. So yeah, he actually has data on the crack growth rate, and this is useful because if you have different size of solders, it may be important for you to know how long you have. If you have a very big solder, then the crack growth rate, it'll take longer for the crack to go all the way across. If I have a smaller solder, then it's faster. So for different diameters of solders, if we have data on crack growth rate or the crack length, which I guess the crack growth rate is the slope of this curve here, then it allows us to predict how long it takes for that solder joint to be completely failed. He also did this for this idea of crack initiation. So in the beginning, when you have, in some cases here, it took a few hundred cycles. He also has data on how many cycles it took for a crack to start to grow. So this tells you that, maybe in certain conditions, your solder is just very robust. It won't crack because there's no crack for it to grow into. So this is the most accurate uh, and most obviously complex set of experiments that was done. And once you have this, then you have a function of crack growth rate versus the simulation result. So given a particular simulation, I can say, well, if my simulation is showing a inelastic string energy density in the crack region to be 100, that tells me that the crack will grow at 1 to 300 micro inches per cycle. And if I know how big my solder ball is, I can adjust for it accordingly. So this is a very valuable data. The other option, a much faster way, is just have some sort of automatic failure detection. So you may have a package with a few hundred balls on it, and each ball would have a different amount of strain. So you can measure which connection fails automatically. So rather than segmenting and measuring the crack length for each solder ball, here we can just we can see when that signal failed. So this doesn't tell you how fast the crack is growing, but it tells you how long it takes for the crack to grow through the entire solder ball, um, or when failure occurs, which could be intermittent failure, I guess. So this is another method of here we have the mean life. So rather than trying to figure out how fast the crack is growing, here we're just saying when does it fail, and then the simulation says accumulated strain or energy density. This is the first graph I showed earlier. And this is also really useful because it's the same idea of if I have a value of 1 for the energy density, then I know that my for this particular package will last 1,000 cycles. Um, What's missing here though is that if I make my solder ball much larger or smaller, right? If I start to adjust the pitch of my solder ball, then the numbers here could change, and I would need to do additional testing to say, okay, for this particular size of solder ball, then um, the mean life cycle will change. So depending on how often you do these type of analysis, the variation in your packaging, if you're always working on the same size of solder balls, then this is a great method of characterizing it because it's very fast. It's much faster than the other way. But if you want to make like a generic model that applies to this solder for all sizes of BGAs, then we would need to do more testing. So again, depending on what kind of correlation and facilities you have available, 1 or 2 may be useful. Um, So let's see. I have a question here. Characteristic length in thermal cycles done. Yes, yeah. This was done. So every point here was an experimental value, and then the lines you see are the equations that Dr. Darveaux uh, fit to the data, and that then allows them to get this. So then you get these points. So they're kind of all match each other. So there's different assemblies here, and you get a curve, and this is the data that then you can use for simulation for any side of solder balls. Okay. So cycles to failure calculation. Um, there's a couple of them here. So you can see Saeed, who's the colleague of Dr. Darveaux, I believe. Um, he wrote some. I guess it should be Dr. Saeed. I'm sure they all have PhDs at Amcor. Uh, So this is his work. So he established a pretty straightforward correlation. Number of cycles of failure is equal to a constant times either the strain or the work or the energy density. So creep strain or energy density. So all you need is to get this the coefficient, and off you go, right? And he did for Nun's model for the material he did. I think this is for SAC. Yeah, so tin, silver, copper, SAC 305, I believe, maybe. He established a couple of coefficients, and you can use that for fatigue calculations for solder balls of roughly that size. I think if the solder ball gets much bigger, then these type of correlations begins to break down. If it's much smaller, same thing. From the original paper back in 2000 from Dr. Darveaux, right? They did crack initiation. So he has a coefficient K1 and K2 to measure crack initiation. He also have K3 and K4 for crack growth. So the characteristic life is if you add the two together and you can divide it by how big your solder is. So you can see this is a much more extensive, rather than a single value here, you have four coefficients that allows you to calculate what what the characteristic life is for the solder that Darveaux worked on. Obviously, the limitation is that he did this work on leaded solder, and almost none of us use that these days. So there are other solder models available. These are kind of the published work, and this is considered, based on my experience, what most of the people are doing. So if you look at the main packaging house, the people that develop high power microprocessors and chips, almost everyone uses this method for solder joint analysis for high temperature cycle. But not everyone does very high power systems, right? Some of us use very low power devices that never get too hot, or maybe maybe you want to look at thermocycling of a board that goes into a harsh environment, but it's not necessarily from self-heating. In that case, there are other solder fatigue models available, and I grabbed this from Wikipedia. It has a good overview, so you don't always have to go to the most advanced model. If you are looking at correlation-based fatigue evaluations, like if you want to compare, hey, I want to change from one PCB to another, or if I want to change from make my solder balls bigger or smaller, how does that affect my durability? You can get some pretty decent estimates using these other methods. So Coffin Mason is a standard fatigue calculation. Cycles of failure is just a function of means the strain range and the mean stress. So this doesn't include creep, which means you don't have to get the full detailed viscoplasticity model. But obviously, it also prevents you from and you would have to do this type of correlation yourself, right? You can do a very simple either analytical or simulation data to get strain and stress, and then try to figure out, if you do enough experiments, you can figure out what all the coefficients are and try to use that in the future for your fatigue calculation. There's another model called the Engelmeyer model, which is the cycles of failure as a function of the strain range, mean temperature, and cycling frequency. So these are often done not even with simulation, right? You can estimate algebraically for a particular solder size what the strain is. So if you can estimate what the strain is, then you can, if you have test data, or if you can find test data on how long it takes for things to fail at different strain, temperature, and cycling frequency, you can fit into these coefficients and start to get estimates of what the data is. Obviously, these models are all established for particular types of packages. These methods are typically really good for if you're looking at more simple packages. So I think someone mentioned QFN. That may be a basic package you may be interested in, or resistors, capacitors, uh, leadless devices, surface-mounted systems. You can probably estimate the strain. Not probably. I know you can estimate the strain pretty easily, and you can fit these into the coefficients and get the results. Similarly, Plateau was part of Dr. Plateau was part of DFR Solutions, which was acquired by Ansys recently. He was able to extend the Engelmeyer model and kind of fit it with Saeed's estimates. So in addition to looking at just the shear strain, he was able to calculate using algebraic methods, calculate based on the size of your package, the size of the solder, the relative CTE mismatch. We can kind of use algebraic methods to calculate what the shear strain and shear stresses are through a thermal cycle. From that, we can calculate the amount of work done, and then you can kind of plug that into this delta W here and try to get the same type of result. So um, fatigue is always going to be something you match to experimental data, and that's what was done for these methods. I want to say that the plateau model is available in Ansys Sherlock, and this is the method we use in Sherlock to do system board level thermal reliability. If you look at the type of details that was needed to be done to model just a very simple BGA, right? We need to model the solder balls and slice it up appropriately. Imagine we expand that to a whole board with potentially thousands of balls on maybe dozens of chips or more. It becomes very computationally expensive to run these simulations. So models like the Engelmeyer and Plateau model, which is available in Sherlock, allows us to look at the whole board and quickly evaluate the reliability of all the solder joints on things like capacitors and resistors of different size and QFN and other leadless devices. We want to save this type of detailed modeling for CPUs and BGAs that are very crucial. And if you look at CPUs and BGAs, they're very different, right? They're not just typically surface mounted and lefted. Oftentimes there's heat sinks attached to it. There's clamping force to ensure enough pressure is applied to it. So the loading becomes very complicated. Not necessarily just from thermal expansion coefficient mismatch. So that's another area that we want to focus on. So the point of this last part is that there are simpler models available for simpler problems. When you look at advanced solder joint reliability on complicated models, the focus of this presentation was really on Dr. Darveaux's work back in 2000 and how we can calculate crack initiation growth from this. I actually think this was done a little bit before 2000. This may be the second set of presentations he did. That's kind of the focus of the discussion here. I see a few more questions came in. Have I done correlations with testing? That's a good question. I was at Ansys for 13 years, and at Ansys we don't have any test equipment, so I only do the simulation side. If anyone's interested in doing this type of correlation and you have test data, this is if you're serious about solder joint reliability, then you should do the Darveaux method, and I can certainly help with testing. If you're kind of buying chips and you want to put it on boards and you want to see for given conditions maybe what the impact of a high reliability board or what the impact of more high reliability solder will be on your system, I would recommend you use tools like Ansys Sherlock and use these type of algebraic equations instead of doing the full simulation of solder balls like here. So it depends on how much detail you want, what your goals are, And obviously, I'm happy to talk to anyone if you have questions. Just send us a email at info@singularityengine.com. Do you think using cohesive models to represent energy? Yeah, so I think cohesive zone models and looking at solder joint from a fracture mechanics perspective is very promising. Obviously, if you look at the failures, it's definitely fracture mechanics related, right? So it is a crack that grows through it. It's an interfacial crack often. In this case, it kind of goes through the solder. And I've talked to people that wants to know what happens if the crack grows in the middle of the solder, near the top interface, near the bottom interface. We can handle all of that with fracture mechanics, and I think it's a great method. I haven't seen a lot of papers to establish the type of correlation needed, but I think it's definitely a very promising area to look into, because I'm sure you can find correlations like this using the fracture mechanics methods as well. Does Sherlock have an educational license option? I don't know. I'm not sure if it has an educational option. There's a lot of papers published on the Ansys Sherlock website though. So if you want more details on extensively on how they use these methods and what the coefficients came from, everything is published, so it's very open. If you're doing educational work for this side, for this type of calculation, you may want to do the calculations yourself, right? To try to get a good feel for what the coefficients are. Sherlock also has a whole host of capabilities on vibrational durability analysis, which requires a lot of simulation. Right? So on the thermal solder joint fatigue side, Sherlock's method, I think, for evaluating large board is great. It's very fast and allows you to get good estimates on simple packages. Um, Sherlock has a whole set of capability on shock and vibration, which if you put any electronics in moving systems, vehicles, cars, airplanes, rockets, you definitely want to do those type of analysis. And they have a very finite element simulation based treatment for that. Um, Looks like we're running a little bit low on time here. And I was having trouble getting um, my simulation screen share working properly, but I was going to go through a short demo of the process of setting up one of these simulations in Ansys. But I think I have another video on that. I'll link that to the bottom of this presentation as well, so you can take a look at that. So I have another video on solder joint reliability that goes through the process of setting up this model, splitting the solder ball into the right size and putting in the data, the material property, and running the simulation. It's pretty straightforward, but I think the main thing out of that is that you want to mesh things carefully and don't use any contact elements. Make sure you have all of your mesh near the solder node to node matched, and then the results comes out very accurately. I've verified all of Dr. Darveaux's models that he published, and as is accurate then, it's still accurate now. So we're pretty confident in getting these right results. I think that's it. If anyone has any questions, again, you can reach me at Singularity Engineering. Let's go to the top there. Oh, there we go. Yeah, so if you go to our website, singularityeng.com, feel free to contact us if you have any questions, if you want to discuss this further. Do you have any reference for the geometry of the packages in solder to set up an FEA? Yeah, so the geometry is the Dr. Darveaux's paper has the geometry, so you have to draw it. It's uh it's good practice anyways. But I do have a geometry available and webinar recording available. Yeah, so this webinar is all of our um, YouTube live webinars are available. It's always going to be on YouTube, and you can access it anytime. So feel free to share with others. Love to meet other people who are interested in solder joint reliability. All right. Any other questions? I'll give it a couple more minutes, but otherwise, thank you all for your time. Pleasure to have you sit with me for the last hour talking about solder joints. If you have any questions, reach out to us at Singularity All right, thanks. Let me stop the stream now.